Okay, we're on week 6, so we are very nearly to the end of our abbreviated semester here. Just week 6, 7, and 8 left. Okay, so this week we are moving into, guess what I'd like to call the meat and potatoes of statistics. So we've kind of done the setup. We are right. We use random variables as models for our data, and so the mathematics behind random variables allows us to build more complicated models and functions, uh, such as the sample mean or sample variance. Then using that can enable us to then figure out what a random variable for like a sample mean might look like. And then once we know what the random variable is, we can make probability statements about it. This week is a little bit more about that, and a little bit more about sampling. So that's really the mechanism for collecting data, and there's some assumptions with it, and that's how kind of all of this stuff works. So there are 3 presentations for this week. One of them I will not go through with you. I'll let you just review that on your own. It just kind of talks a little bit more about data collection than than this presentation. This is really kind of our key, however. So this this time we're talking sampling distributions and we're talking the central limit theorem. So that's our big payoff at the end of this. So we'll start with samples and populations. We'll discuss sampling. We'll discuss sampling distributions, and then we'll talk central limit theorem. Samples and populations. So first of all, we have the target population. In a statistical setting, that is the totality of elements under consideration about which information is desired. So that's what we want to know about. An example could be if we're interested in the price of a gallon of regular gasoline in the US on a given date, the population would be all prices from all stations in the US for regular gas on that date. Or example two, we're interested in the speed of light, then the population would be the notional infinite set of all possible measurements for the speed of light. Now, the population need not be a concrete set of things, as in the first example, but it does need to be capable of being well defined. And both example one and example two are well defined. Okay. This population has an underlying distribution, and it's that distribution that we're interested in. Right? Every population distribution has parameters. Now, if we're sampling from a normal population, those parameters are the mean or the variance. So the mean mu variance sigma squared. For an exponential population, if we're sampling from an exponential population, then it would be the mean lambda or the rate. So I think I got those reversed, right? So the mean, usually we use theta to represent that rate. We usually use lambda to represent that, but I think you get the idea. It's either impractical or impossible to look at the entire population. All right. Since we can't look at the entire population, we instead look at a subset of that population, and that's called the sample. If the sample's collected correctly, we can use it to infer things about population as a whole. In particular, we would like to have what we call an IID sample, or equivalently a random sample. Okay. This is a sample. So IID means, as you see in the point right below, independent and identically distributed. Okay. Whether we call it IID, we call it random, it is a sample chosen so that each element of the sample has the same distribution. In other words, from the same population. And the elements of the sample are pulled from the population independent. Okay. A sample chosen with these properties is independent and identically distributed, and the sample has statistics then that will correspond to the population parameters. So let's next talk a little bit about sampling. Okay, so we're talking sampling. We'll talk sampling strategies. Okay, now the crucial element here for any type of sampling strategy is that it needs to involve an element of randomness. Okay, now in your next presentation, we'll talk about a non-probability sample, and there are times when you're kind of stuck with that. Um, uh, that's fine. Ideally, though, um, no. So you want to have an element of randomness, and that's crucial because what we're really after for the math to work is we need what's called a probability sample. That's where every element of the population has a known chance of being in the sample. Okay, so every element of the population has a chance of being in the sample. And in theory, you can calculate that probability. There are several basic methods of probability sampling. The three most common are simple random sampling, systematic sampling, and stratified sampling. Sometimes, however, we don't have a choice in the sampling strategy. Typically, in statistical consulting anyway, or in uh, my own field, I do statistical work, statistical consulting um, for the Defense Department. Most of the time, I'm just given a data set. Okay, so most of the time we might be handed a data set, and we may not be able to determine how that data set was collected. Okay, we try, right? So when somebody gives me a data set, I do what I can, try and understand where did the data come from, how did you put it together, and try and kind of understand, was it collected in the right way. Sometimes though, you have none of that information, you're just handed a data set, so you have to make some assumptions, right? Instead of a probability sample, you might have a non-probability sample, which means there could be biases in the analysis due to the sampling method. But if you have no way of knowing what those are, you have no way of adjusting, right? So we're going to mostly, for this class, mostly assume the ideal setting, which is that things have worked out. We have gotten probability sample, and so our math works. Okay, so we'll start with simple random sampling. The population in simple random sampling is not divided up in any way. So all subsets of the population are given equal probability. That means every member of the population has an equal chance of being selected for the sample. And that also then means every pair in the population has an equal chance of being selected, as does every triple, and so on. This property minimizes bias and simplifies the analysis. Right? Sounds good, but it does have its problems. The randomness of the selection can result in over or under sampling some subgroups. Not dividing the population into subgroups means you cannot make inferences specific to the subgroups. It can be cumbersome when sampling from a large target population. Right? You need to have a large enough sample to make sure you've got a good view of the population, and that can be expensive. So what do we mean by over or under sampling some subgroups? Give you an example of political polling, for example, right? So if you just do a pure random sample in political polling, a simple random sample, then odds are you're going to get oversampling from places where there's large concentrations of people, like say uh, urban areas or or California, for example, which is the largest population in in the United States. If you just sheer random chance of selecting a name for a ballot question, for example, you will likely oversample urban areas on the coast because that's where a lot of the people, right? And that's for a presidential or congressional election, for example, that's not going to really give you a good indication of how things are going to shake out on a national. So, or if you don't want to talk politics, think about if you're, if you're trying to do, maybe you're trying to determine the prevalence of a certain fish disease, like whirling disease or something like that, for example. Well, if you're just doing simple random sampling of fish catches, what you're going to get is uh, oversampling from where people are catching the most fish. And that's not going to really tell you, that's going to be in places near reservoirs and things like that very often, um, like Colorado, for example. And that's not really going to give you an indication of how the whole state looks. You're going to oversample certain areas. Okay. So if that is, uh, if that is a problem, there is a way to deal with it. We'll talk about that in a second. But first, let's deal with that sampling from a large population idea. Um, that is systematic sampling. Okay. We order the target population in some way and select elements at regular intervals through the order list. So, for example, maybe I'm interested in collecting a uh, market sample for, um, I don't know, Miami, and so I want to call people to perform my sample. So I'll take what we used to call a phone book. So we'll take the phone directory of all the names. We'll pick a random starting point, and then we'll do every 100th name. And we'll go through that till we get the size sample we want. Okay. So that means we randomly pick a starting point. The reason that's essential is so that every element of the population has a chance of being in the sample. We start with the first person and do every 10th, well, then the second, third, fourth, and so on people never have a chance of being included. If we randomly pick our starting point, then every element in the population has a chance of being in. Every kth element from the ordered population is then selected for the sample. What's great about this, it's easy to implement, it's efficient. What's not so great is that it is especially susceptible to periodicities in the data, right? So if you have um, a periodic effect that affects every, you know, fifth person or something, and you might miss that effect. It can also miss inherent dependencies in the data. So, for example, if we sample every 10th house in a neighborhood, we miss the effect of a house on its immediate neighbors because we're not sampling. Okay, so that's systematic sampling. Stratified sampling is where we try and deal with all of the drawbacks of simple random sampling, of um, not being able to make inferences about subgroups and ensuring we don't oversample certain subgroups, and that's stratified sampling. We break the population into subgroups or strata, another word for it, and we do a simple random sample within each subgroup. Okay. So population is divided into subgroups. Each subgroup is then treated as an independent subpopulation. and a random sample collected from each subgroup. By breaking the population into subgroups, that allows us to make inferences about each subgroup. It can improve the efficiency of estimation because we avoid the over or undersampling issues. The drawbacks are, well, identifying the relevant strata might be costly, right? If you don't know that a type of subgroup is important, you don't know to divide up and look for it. Ensuring all of them are sampled can also be costly, right? And it can be very difficult to implement that. Okay. Um, let's now talk sampling distributions. So we've seen this before. This is our basic paradigm, it's our basic setup. We have a population. That's what I care about. It has parameters. That's what I'd like to know. Well, I can't directly get at those, so instead I perform sampling of some sort, the methods we just talked about, to get a sample. I perform estimation on that sample to produce statistics. I want to use those statistics to make inferences about the corresponding parameters. Okay, so we calculate a statistic from the sample to estimate the corresponding population parameter. The question for sampling distributions is, how much would the statistics value change if we took a different sample? What we're after here is the sampling distribution of the statistic, distribution of values taken by the statistic in all possible samples of size n from the same population. Let's build a notional sampling distribution of the sample mean so we see what we mean here. We want the distribution of values taken by the sample mean x bar in all possible samples of size n from the same population. The model assumption is that our observations x sub I are sampled from a population with mean mu, variance sigma squared. So what we're doing here, so what we want to know about is that unknown population parameter mu. Okay, if I take a sample of size n and I calculate the sample mean, I'm going to get a number. If I do another sample, sample 2 of size n, calculate another sample mean, I'm going to get another number, very likely a different x bar. And if I do that over and over again, I'm going to get a bunch of values for the sample. Question is, what is the distribution of those values? All right, so let's look at an example to illustrate this concept. We're going to suppose that we have a fair die, and we're going to throw that infinitely many times, with the random variable x being the number of spots we get on any throw, right? The value for any throw. Probability distribution of x is then, right, the probability we roll 1 is 1/6, 2, 1/6, 3, 4, 5, everything is 1/6. The mean and variance are calculated, right? We know how to do that from earlier. The mean works out to be 3.5. The variance works out to be 2.92. The standard deviation, just the square root of that, is 1.71. Okay. So note the following. A sampling distribution is created by looking at all samples, and we'll look at samples of size 2 dice, for example, and their mean. So we could roll a 1 and a 1. That would give us a sample mean of 1. We could roll a 1 and a 2. That would give us a sample mean of 1.5, and so on. So you see here the sample, the value for one dice, value for the second, what the sample mean would be. We could do that for all possible rolls of the 2 dice in the sample mean we get. And we notice that while there are 36 possible samples of size 2, only 11 values for the sample mean x bar. And some of those values, such as 3.5, occur more frequently than the other values, like 1, for example. The sampling distribution of x bar is shown here. Okay, so this is the histogram we put together from this. Okay, so here's the value of X bar, 1.0. The probability that we get that value for X bar is 136. So we can put that together for all of the values of X bar. And you see we get a histogram that looks like this. And the mean of this distribution is 3.5, and its variance is 1.46, or the standard deviation 1.21. And so let's compare the distribution of X, the random variable itself, where everything was equally probable, with the sampling distribution of the sample mean X bar. Right? They're not the same thing. And we note also that the mean of the sampling distribution of X bar is the same as the mean of the original random variable. The mu of X bar equals mu, and we note that the variance of the sampling distribution of the sample is half of the original population variance. It's sigma squared over 2. We generalize the mean and variance of the sampling of 2 dice, right? Mu of X bar is mu. Sigma squared X bar is sigma squared over 2 to n dice, with the mean of the sampling distribution of the sample mean for samples of size n is still the population mean mu, and the standard deviation for the sample mean, sampling distribution of the sample mean, is going to be the population variance, the population variance divided by the sample size n. The standard deviation then would be the standard deviation of the population divided by the square root of the sample size. That is called the standard error. Okay, so the standard deviation of the sampling distribution of the mean is called the standard error, sigma over square root of n. So the center of the sampling distribution for the sample mean is the unknown population. And the variance of the sampling distribution of the sample mean is the population variance divided by the sample size. All right, so we know the mean, we know the variance for this thing, but what kind of distribution is the sampling distribution of the mean? Well, you may notice in our example that what comes out is symmetrical. Symmetrical with a peak at the population mean. If we repeat our experiment, this time we do samples of size 1,000, and we crank that out a bunch, we notice that we have that same symmetric shape, just like we did for n equals 2. So if we look at the distribution of the mean with sample sizes as n increases towards infinity, we would continue to see the same distribution shape, the same symmetrical distribution with a peak at 3.5. That result, we're going to generalize into what we call the central limit. The distribution shape for our sampling distribution of the mean is a normal distribution. Okay. Most statistical inference relies on the central limit theorem, or sometimes we abbreviate it CLT. The setup for the central limit theorem is straightforward. We have a sequence of independent random variables, x1, x2, and so on, where the x sub I each have a common but arbitrary distribution with a mean mu and a variance sigma squared that we assume is finite. Okay. Note that these conditions are met. This is exactly what we have. We have a random sample. So if we have a sample that's IID, independent and identically distributed, then we have the setup central limit. Okay. Then, if that is the case, then the square root of n times the sample mean, 1 over n times the sum from I equals 1 to n of xi, that's just the sample mean, minus the population mean, converges in distribution to a normal with mean 0 and variance sigma squared. All right, well, you do an example using the central limit theorem. We have a population with a mean of 82. a standard deviation 12, a random sample of size 64 is selected. What's the probability the sample mean will lie between 80.8 and 83.2? Well, we have mu equals 82 and sigma equals 12 for our population parameters. N equals 64 here. The central limit theorem tells us the distribution of the sample mean is going to be approximately normal with an expected value of 82. That's the population mean. And a standard deviation of the population standard deviation divided by the square root of sample size. So that'd be 10 over the square root of 64, which would be 1.5. So converting to a standardized variable, we have x bar minus mu divided by sigma over root n. That's x bar minus 82 over 1.5. That's going to be a standard normal, right? So the probability a standard normal is between negative 0.8, positive 0.8, works out to be 0.5762. All right, so in simple terms, what does the central limit theorem mean? What do we mean by large enough? Well, with a large enough sample size, sampling distribution of the mean will be approximately normal regardless of the population distribution. That means we can use the properties of a normal distribution to make inferences about our population mean. The rule of thumb on large enough is generally the sample size should be larger than 30, but there's some buts here. If the population distribution is far from normal, heavily skewed or sharply peaked, flat, bimodal, for example, then you might need a much larger sample size. And if the sample is not independent, the central limit theorem may not apply at all. So one example of this is the normal approximation of the binomial, which I believe we've mentioned before. The binomial random variable then, x is binomial with n and p is the parameters. With n large enough, the binomial PDF isn't too, and if the binomial PDF isn't too skewed, then x approximately follows a normal distribution with the mean and variance NP and NP1 minus P respectively. Large enough and not too skewed, depends on how good an approximation you want. Various rules of thumb, but the easiest, I think, is that you want both NP and NP 1 minus P to be bigger than 10. But even when those conditions aren't met, such as N equals 6, P equals 0.5, right, then NP is 3. You notice that it's still not that bad, right? Here's the normal PDF. Here's the binomial. It's not horrible. All right. So sampling distributions. Oops. For proportion. So we can use that normal approximation for the binomial for cases when we have samples from a binomial experiment. The most common of these is going to be the polling idea, right? Which candidate you support or what. So that's the most common case. You're going to see that all the time. We can use the normal approximation here. Binomial random variable x follows a binomial with n and p, approximately distributed as a normal with mean NP and variance NP1 minus P. So that would mean if x sub s is the number of successes for our sample, the sample proportion is P sub s, that's just x over n. P sub s minus P divided by the square root of P1 minus P over n approximately is a standard norm. Okay, central limit theorem gives us a distribution for the sample mean, provided the sample is independent, the variance is finite. The sample mean approximately follows a normal distribution, right? X bar is approximately normal with a mean of mu and a variance of sigma squared over n. But this distribution requires us to know the population variance. Thing is, if we don't know the population mean, how would we know the variance? So instead, we must estimate sigma using the sample variance. right? S squared, that's 1 over n minus 1 times the sum of x bar minus, sorry, x sub I minus x bar squared. When n is large, this doesn't matter much. With smaller n, it can have a significant impact. So for small samples, as before, we have a sequence of independent random variables where the xi each have a common distribution. Now we let t be x bar minus mu divided by s square root of n. If the x sub I follow a normal distribution, t follows what's called the student's t distribution. I think I mentioned that before. As the degrees of freedom go to infinity, our t distribution becomes the standard normal distribution. If n is small and the population is not normal, you're out of luck. If n is large, then we can use the central limit theorem. Real quick, the student t, symmetric, bell-shaped, related to the normal, heavier tails. T distribution has a single parameter called nu, which is just the degrees of freedom, depends on the sample size. The mean of the t distribution is 0. The variance is nu over nu minus 2. That's what it looks like, where that is the gamma function. And here, the student t distribution compared to when the degrees of freedom are infinite, that is the standard normal. And you see the tails are heavier, but it very quickly starts to approach the standard normal. By 36, you really can't distinguish the curves anymore without zooming in. Okay, so it really quickly gets there. Sampling distribution of the variance. For the sample variance, we again assume we have a normal distribution. We have a sequence of independent random variables, x1 to xn, mean, mu, variance, sigma squared. If s squared is our sample variance, then if we make a new random variable v, that's n minus 1 times s squared over sigma squared. That follows what's called a chi-square distribution on n minus 1 degrees of freedom. Okay, I think we mentioned that one before. A little bit about the chi-square. It's related to the sample variance, right? And it's just a special case of a gamma. We talked about gamma random variables in chapter 5, I think. This is just a special case of this. So if we have independent, identically distributed realizations from a standard normal, and we sum their squares, that's our chi-square. So chi-square defined for positive number only. There's the PDF. Mean K, variance is 2K. That's degrees of freedom. And just to get an idea what they look like, it's asymmetric, as you can see, and you can see how it looks similar to your gamma. The F distribution is our other key sampling distribution. It arises when comparing variances. It's the ratio of two chi-squared. So if U is a chi-squared with m degrees of freedom, V is a chi-squared with n degrees of freedom, then U over m divided by V over n is an F distribution on m and n degrees of freedom. There's the PDF where that B is the beta function. And this is what the different F's look like. All right, so sampling distributions allow us to make inferences. Knowing what the sampling distribution is allows us to make probability statements about the population parameters of interest. In particular, the population mean, but also using the chi-square and F, we will be able to do the variance. These probability statements in turn will allow us to construct reasonable likely intervals for our population parameters. Those are the confidence intervals. And those in turn allow us to construct hypothesis tests for those parameters. All right, that is it for this section. Let me know if you have any questions.